Okay. Okay, so today, the third one of the day, okay, so I wanted to start again with the local duality statement, because after all that stuff, now we're finally there. And I want to sort of milk it a little bit to see what we thought. Let's just recall what we have here. We have, for I greater than or equal to 1, we have a statement of that the whole cohomology module is some graded dual of this thing. So it's just turned upside down for an X module. And therefore you can get the dimension of any given one piece if you're interested. Except for H0. H0 you only have up to sort of an extension here. You don't have it on the nose. And that's sometimes okay, sometimes not okay. So we'll for now think it's okay, and then we'll get back to that later.
Why is it called local duality?
Because there's also a global duality with global X. I don't know. It's one of the many versions of Serre duality. In fact, this was Serre's original proof of one of the original proofs. What?
Global X meaning what sheet?
Sorry, what?
So the global X meaning.
Yeah, global X. So there's also a version which I'll say something about, although not in quite in that form, where instead of these X are considered local X because these are like sheaf X. If you want, they're modules and they restrict under localization and everything is nice. But you could also have global X, which is a vector space, and that's it. And then there's also a version for that, which is also useful, but not for this kind of, not for this. Okay, so let's go back to it. I promise this is the last rational quartic one for a little while. We'll do slightly more interesting ones. Do you remember the rational quartic? We actually, after a little faltering, got the X modules for this morning. We had X2 was actually sort of complicated. I think it had 3 generators and 6 relations or something like this. It wasn't that complicated. It was still a linear matrix. But it was, in any case, something like that. X3 was just a copy of the field K in degree. Well, actually, we're now shifting by S of -4 here. Last time we were doing S. So this is all shifted off of degree. And that puts this element K in degree -1. Right. Okay. And all the other X's are 0. So let's just see what that says in terms of all of this, just to sort of play around with it. Let's look at the bottom sequence first. So the xn plus 1, n here is equal to, we're in P3, so n is 3. So that's x4, that's 0 here. Okay, so there is no x4. On the other hand, x3 is not 0. So what we get is we have the module S, oops, that's S mod I. Okay, so this is an S modulo I here. And that maps to H0 lower star of S mod I tilde, which was O of X also. But it's not isomorphic. There's an extra guy there, K. That guy was in degree. You can go nuts with these degrees, by the way. After a while, you start dualizing, and it's sort of like you dualize too many times. Instead of twice, you dualize 3 times or 4, something like this. But here, that guy's in degree -1, so this is in degree 1. So that says that H0 of O of X in degree 1, so that's H0 O X of 1, has dimension not 4, which is the dimension of S mod I in degree 1, but an extra guy because of that. And that's because of the missing S squared T squared term. So we were embedding by a not complete linear series, if you're familiar with this stuff, and it's detecting that information. Later on, we'll see how to pick up that S squared T squared, but not today. And in fact, we probably won't do it on the rational quartic because I'm getting tired of the rational quartic already. Okay, so the other thing is that, how about all these other x's here? Well, if you think about it, all the ones, this is a curve, and because of the statements I said earlier about which x's have to be 0 outside of the codimension and the projective dimension, that tells you that the hi's have to be 0 for I greater than the dimension right off the bat. So anyway, that's this statement I is greater than or equal to 2. And H1 lower star O of X is a relatively complicated module, but in fact that's what we'll see next time is the canonical bundle. of the curve. Okay. There's a special case I wanted to consider here. Is the case when M is Cohen-Macaulay. Remember, Cohen-Macaulay meant that there was one non-zero X module. And a particular very important case of this is the module M is S modulo a complete intersection. So something that has codimension exactly the number of equations that you have, and homogeneous. So that's an important one. And here is the free resolution. I'll let C be the codimension, so that's how far the resolution goes. That's the projective dimension. And now we can compute all these various H i's of M tilde. H0 of M tilde, it usually would use xn and xn plus 1, but those are both 0 because the length of the resolution is short enough. I guess I should say that this is a complete intersection of things of dimension higher than 0. Okay, it's not a set of points because otherwise it would be an xn term. Then all the other ones, xn minus 1, all the way down to x of, before you get to x to c, those are all 0. That translates into the h1 of m tilde up to h of the dimension of m minus 1, m tilde being 0. And then you have one non-zero thing at the very end. So it's pretty good. So for any of these Cohen-Macaulay things, you've got m on the nose. You've got the best possible presentation of your m tilde somehow, because it's already equal to the whole h0 lower star of it. The others are 0, then you have the top guy, which turns out is the canonical module. And that's also very nice. So in this case, it's pretty good. Any questions about this stuff? I'm going to do two more corollaries, very simple corollaries. Well, one is simple, one's a little less simple, of local duality, and then we'll move on to an example. This one is sort of slightly more general situation than that. I don't know where. Anyway, so suppose that we have a finally generated graded S module, and we're interested in M tilde, as usual in all of this. Suppose the projective dimension is less than or equal to n minus 1. Remember, n plus 1 is the number of variables, so this is 2 off. That means that xn and xn plus 1 have to be 0, and so at least that first statement there is still true. Because of the exact sequence from local duality, we have m is isomorphic to h0 lower star of m tilde. And in particular, you can calculate the h0 of m tilde by just looking at the degree 0 part of the module that you had in your hand, which is the best situation. What this really means is that if you look at the resolution and it's short enough, you already have a good presentation of your module in hand, and so you don't have to try to do things to improve it. Later on, we'll talk about improving things like that. Okay, here's another corollary, which is a little more interesting. There's this issue of when is h0 lower star of m tilde. I said it could be infinitely generated. And I meant it could be infinitely generated. Okay? So the question is when you don't want to, you would like to be in a situation when that's not the case. So let's take a look at this. So the statement I claim that follows from this local duality is the following. This module is finitely generated, which always, in this context, just means that for large enough negative degrees, it's 0. Okay? So it can't go off infinitely. There can't be things in it for negative enough degrees. Okay, so anyway, it's finitely generated if and only if you look at, say m is equal to s modulo I, I'm just looking at all the components, the associated primes of that ideal, or the components of it, and as long as all those guys have dimension at least 1 in projective space, then in fact that thing is finitely generated. And the proof is except for one little piece, it follows immediately from what we just did. So it's finitely generated if and only if what? Well, let me bring the local duality statement up. how could h0 of m star of m tilde fail to be finitely generated? This guy here is a submodule of m. M started out finitely generated, so that can't mess things up. Okay? Then we have this going to there. The only way that it can be a problem is if this thing is non-zero in all negative degrees. Okay? So that's what the next statement is. If it's non, and actually because of the check, it's a regular. Without the check, this is is just a finitely generated graded module. So it looks like this. It starts in some degree, and then it has things going on up, possibly infinitely far. When you do the check, you're just turning the picture upside down. So there's some top degree where it's non-zero, and then it goes down, and maybe it stops or not. It stops exactly when this is a finite dimensional vector space over K. So that's the next statement. That's if and only if this xn of m comma s, I can do it s twisted by the minus n minus 1 or not. It's still the same statement. It's finite dimensional. Well, actually, to say that that's finite dimensional means that the codimension as a module is actually equal to as large as it can be. It's the n plus 1. Now that there's this statement, that kind of thing is handled and is very useful a lot of times in computational algebra, is this statement by Eisenbud, Hünicke, and Vasconcelos. There's a lot of interesting stuff that goes on in here. Let's see if I can focus that a little better. So if the codimension of any x I of m into s is always at least I. What's really cool about that, though, is that suppose it's actually equal to I. Then, in fact, all of the components of that thing, of codimension exactly I, came from the original m here. I think of it in my mind as s mod I, but it's m. So somehow all these associated primes, which could be embedded components or really nasty stuff, they sort of bubble to the top, and they're right there. However, but we're given that the codimension is n plus 1, and this thing has codimension at least n instead. So to say that its codimension is n plus 1 means it doesn't have any codimension n components. What's a codimension n component in Pn? Point. Okay, so that means as long as it doesn't have, it's not supported on any points, then it's okay. And that's the boom. So anyway, so this is saying this is good. So points are bad is as far as this goes, but otherwise this thing is at least a finitely generated module, and you can hope to get the whole thing. Any questions? It's a quiet afternoon. Okay, so let's see. Okay, that's enough of that for the time being. So what I want to do is I want to go on and do an example and basically consider the sheaf of differential forms and cotangent sheaf, like higher powers and stuff like that. So let's do this. When you first learn about the sheaf of differentials, well, it depends on how you learn it, okay? So everyone comes from slightly different backgrounds. But in affine space, this is easy, right? If you're in affine n space, the module of differentials is given by dx1 up to dxn. Just differentials like this. And if you have if you're modulo an ideal, then you're going to take those things and mod out by the df's for any f in your ideal. That's going to be what we're trying to do. This we'll try to do a sort of a similar thing. Okay. So on projective space, there are a couple ways of making sheaves on projective space. Suppose you know it locally and you know how it patches around as you go from one open set to the next. You could try to make a sheaf that does that, a module by gluing a lot of these things together. But you'll get a very inefficiently presented module that way. It'll be just huge. This is really a cool statement. This Euler sequence here. This says that, in fact, you can think of omega 1, which are these dx1 and so on, as the kernel of this map just given by the variables, x0 through xn, like this. And the way you can think about this is here. you think of it as on any given ui, it's just generated by all the dxi's that are not including that one. Because on ui, that x1, xi is non-zero, and so you can remove that element of the module here. So you actually, it's actually an amazing thing that it presents this the sheaf of differentials really efficiently. I mean, it's really pretty good. Okay, anyway, so that's a standard sort of sequence. Now, but we're really interested in omega 1 of a projective variety x inside of there. Now, see how we can get that. Okay, again, these are all standard sequences you find, and if you're an algebraic geometer, these are your bread and butter. These two sequences, you use these things with the long exact sequences in cohomology like all the time, every day. Except when you're even when you're on vacation. Okay, so here this is pretty good, and actually this is very intuitive as well. Omega 1x is sitting over there. What are these guys? Omega 1 of Pn, those are the differentials on projective space. So locally you can think of that. And the image is you take the elements of the ideal and you map them into dg, and then you just take the co-kernel with respect to those. And again, if you do this locally on each affine piece, it's just automatic. And the thing is that this gives you a really nice presentation also of this omega 1 of x. Well, except that now we have to figure out what that really means. Okay, because we have all sorts of stuff here, and we have to sort of unwind the definitions. So let's do that. I started at 2:30, right? Yes. Oops. Unwind these. And when you get the following. So suppose we have our variety x, which is a 0 set of I as usual, and the same ring R, same notation as we usually have been using. The cotangent sheaf omega 1 of x, you can actually get as a homology module of rings over R. A module of maps over R. And so you can see what's going on. It's R minus 1 to the n plus 1 to R is just the x0 through xn. That is actually the thing up here. And essentially, now that it's over R is because you tensored it with O of x. Okay? And similarly, the other map, the F is the J from F to R is actually the generator matrix for, that's supposed to be F into S, is the generator matrix for the ideal itself, okay, in S. That's S. And then DJ is the Jacobian of that, and then you just reduce it mod R. So you just think of it modulo of the ideal rather. Okay? And so it's just the kernel of this thing modulo these differentials. And that's it. And that gives you a graded module that presents, whose twiddle is omega 1 of x. Okay? Let's do an example. Uh-oh, it's a quartic. But it's a different quartic. So let's do the Fermat quartic. Okay? So here, let's just take the nice quartic a to the fourth plus b to the fourth plus c to the fourth plus d to the fourth sitting inside a projective 3 space. This is a K3 surface. It's got lots of other interesting properties. You guys probably know a lot more about this than I do. But at any rate, so this is this thing. And we want to find omega 1x, which is going to be some m tilde, and we want to figure that out. And then we'll calculate the various cohomologies of omega 1 of x. So the first thing we do is we actually write down what this thing is in terms of our given equation. There's only one equation, and so its derivatives are a cubed, actually 4a cubed, 4b cubed. I got rid of the 4. Okay, so it's a cubed, b cubed, c cubed, d cubed. And the other one is still a, b, c, d. So the only thing is now, when we calculate kernel, we have to remember that the f that we started with, the a to the fourth up to d to the fourth, is 0 and so on. But There you have that. Okay, in a bit, what we'll do is we'll do this on the computer just to sort of play around with it a little bit. And we'll find that M is actually generated by 6. The reason I want to do it by computer is it shows something slightly interesting that you can actually prove a lot more about this. But you have M, it's generated by 6 generators, all degree 2 elements. Notice, by the way, that says that M itself has nothing in degree 0. Okay? So anyway, so that's that. And then there are 8 first syzygies, and then 2 over here at the end. So actually, before going into the computer, we can see a couple things about this right off the bat. So H0 of omega 1 of x star, the projected dimension is short enough now, right? We're in 4 variables, A, B, C, D, 0, 1, 2, 3. This has projected dimension 2, so it's short enough that the H0 lower star is equal to M. Okay? So in particular, H0 of omega 1 of x is 0 right off the bat. But actually, that's going to happen for all these 10 pi surfaces. But, so you have that. Okay, let's actually put the projector on. And while it's turning on, are there any questions up there? Or any suggestions on how to see? Okay. Let's turn this off for a moment. Okay, can you see that still? Is that okay? Okay, so let's do it over the rationals. And take the polynomial ring S to be the variables A through D. And there's the ideal of that. F is the ideal given by that quartic polynomial. R is the quotient ring. Now I'm going to write down the 2 matrices that we're going to take the homology of. The first one is the variables of S, which is just A, B, C, D, and then tensor it down to R, and we get just the variables over R. The next thing that we want to do is take the Jacobian of F, which is just going to be the one thing, and tensor it back with R, and you get that now with the 4s over there. And now what we want to do, there's a routine for doing homology, which takes 2 maps and just calculates kernel mod image. And so P1, we want the kernel of that mod the image of dj. This will be calculated over R. And we get a subquotient. It's already interesting, okay? So what it says is that the syzygies on those 4 variables, A, B, C, D, modulo the polynomial f, you get the 6 Kazul syzygies here. Those are the first 6 guys here. Those are just the trivial ones that you're going to get in this situation. And you pick up one other one, which, by the way, is essentially this thing, except for the 4. So this is a subquotient. So it's all of these guys modulo that. So there's going to be 6 generators. That one's 0 because it's there. And so we can actually do that. And it turns out that this is completely general. You don't need this to be this particular f here. It could be any f whatsoever of any degree. And it could also be any ideal. Same sort of thing happens. Whoops. Okay, yeah. So M is primitive M. So there's 6 generators. And now something very interesting happens, which you would maybe notice if you actually did it by hand. The first 4 columns is the next matrix in the usual Kazul complex, which are the relations on the 6 Kazul syzygies. And then you pick up another 4 generators, which themselves are a Kazul map on the A cubed, B cubed, C cubed, D cubed. Actually, it's a transposed one if you look at it right. But in any case, you exactly have it. And again, this happens completely generally for any of these things. Okay, now I really need it over S in order to do the whole X thing with the local duality. So let's do that. I'm going to take the presentation of that module, that's just a matrix, and I'm going to lift that back to S. It's going to be exactly the same thing, but now thought of over S. And M is going to be that cokernel. Okay, so this represents omega 1 of X, or does it? I forgot one little thing. Okay, when I just lifted it back, I didn't lift it back, making sure that the polynomial F annihilated everything. So maybe what we should do is make sure that F is the annihilator of this module is F. It should be. So let's see, did I do that? Yeah, good. So annihilator of M, and yep, it is equal to F. Okay. So in fact, normally I might have to throw in, I'd have to throw in new relations with all those F's in there. But it turns out I don't here, and that's actually a general fact as well. At least for hypersurfaces. Okay, now, we can resolve this just to see what this M looks like, because that's actually what we're going to do. And this is the 682 that I had over on the slide over here. Do I actually look at it? Yeah. It's also interesting to look at because the first matrix is the one that we saw earlier. Right, that's the presentation matrix. And then here, the next matrix is actually an extremely simple sort of deal. So that's actually, this kind of thing is nice because then you can all of a sudden maybe really prove things about this rather than just sort of doing it by computer. So H0 of omega is 1. Why is that? Oh, because the Hilbert function, M is everything, and there's nothing there. In fact, it starts in degree 2. Now the x2, which one is x2 giving us? So we're in how many variables? 4? Yeah, we're in P3, right? So x4 and x3 were the stuff around the H0 part. And so x2 is actually giving us the parts of H1 of omega 1 of x. So this is the module x2, and just to compute it, we see here, get that out of the way. It's actually generated by 2 elements as a module, one in degree 0, one in degree -4, and it splits as the sum of 2 nice modules. One of them is S modulo A, B, C, D. The other one is S modulo the cubes of all the variables. And again, this is a fairly common sort of thing. But we want this in degree 0, right? No. We want the, yeah, because I did the S to the -4. So we want, for H1 of omega x here, I want the degree 0 part of this. So I see one of them there, but then this other thing will have some as well. And here's the Hilbert function in degree 0, and it's 20, which is good because that's actually, so that's supposed to be the number for a K3 surface. Okay, what's next? Oh yeah, let's do H2 over omega 1. This is x1. Notice that x1 is still going to be non-zero because M is actually supported on a codimension 1 set. So this has actually got something in it. And again, it's something fairly nice, actually very nice. And the Hilbert function of that in degree 0 is also 0. Okay, so this is pretty good. It gives you the entire cohomology of that and in such a way that you can actually generalize this and write down formulas for it. Any questions on that example? Yeah?
Can you write down the canonical differential?
Omega x, you mean, or kx? Yeah. Yes, and we'll do that next time. Or maybe at the end of this time. There are a couple things you can do along those lines, and we'll probably do both of them. Probably. Now, let's see what we have here. This is just a statement. H1 of omega 1, whoops, let's get rid of this for the moment. Okay. Yeah. Okay, good. So we just saw from the computer example that H1 of omega 1 is 20, and H2 of omega 1 is 0. These are things that you could compute otherwise if you really wanted to from various information from the exact sequences. But it's nice to see you can do it here too. So suppose now I have the following question, which is, I don't know exactly the answer. suppose I take X to be a projective variety, say it's smooth, and we suppose from this process we do exactly what we did above to get this M. Well, when I say exactly what we do, I mean M is, I didn't write it down here. It's you have a presentation of M and given as two Cazul maps, one in the A, B, C, D, and the other one in the derivatives of your polynomial F, okay? Or in all of the generators of I. You have one for each. So when is that particular module, M, that you just wrote down, when does it have projected dimension small enough so that you know that you have all of H0 staring you in the face? Well, it worked for that one. It's certainly not going to work for some things, but it's an interesting question to look at. So we were asked about the canonical class, which is really wedge. So the sheaf of forms of highest size dimension of the variety. So you might want to know how to get that. So suppose, oops. So the situation is, how do you actually find a presentation of omega p of x? I want a module that gives it to me. Well, it turns out that this is actually very, very easy to, at least in principle, give such a thing. Suppose I have a presentation module for my module. Actually, this can be for any true module M. It doesn't have to be omega 1. Suppose I have a presentation matrix for M. F and G here are free modules over S, say. So it's one of the ones we have here. Then wedge P of M has a presentation of the following form. You take wedge P of F, so you take all the exterior P forms on the generators of F, and you take this guy, the P minus 1, the wedge P minus 1 of F, and tensor it with G. Okay? These are all free modules, really nice. You can write them down without any computation within reason. The map here is actually pretty nice too. How do you get there? You take G tensor this guy, you first map it to F tensor wedge P minus 1 of F using the original map phi. So it's the identity on the other half. And then you just wedge the two guys together, and that's the map. And it's an easy thing to sort of do in coordinates, sort of how the poly 2 does it as well. So anyway, this is a presentation of wedge P of M, and actually, everything here is nice, since it's all done via exact sequences, and tilde is an exact functor, sort of, essentially. You have that if M is the M tilde is omega 1, then wedge P of M tilde is omega P. So you have it right away. Okay? That's all very well and fine, except for one little itty-bitty problem. That can be fairly nasty presentation. When I say nasty presentation, we're talking, you might have rough time computing the resolution of it. So you have to deal with that somehow or another. Let me just check and see if I want to wait on the example here. Yeah, okay. Now what I want to do is actually, so now we have the ability of getting all of these omega 1 and omega p and so on. That means we can get the Hodge diamond. I'm going to write it in a way that's more conducive to the way I would print it in Macaulay 2 or something like that. But anyway, oops. So here's the thing with the Hodge diamond. So suppose I have a smooth projective variety, X, of dimension D, and maybe we'll, for the moment, think that that's a threefold. It's dimension 3. Okay? And then we consider the following numbers. HPQ is the dimension of HQ of omega P, X. And we want to basically know all those numbers. So here are all the possible ones you have. It's these 16 numbers right down here. However, there's a lot of symmetry in these, at least if your variety is smooth. Okay, so let's see, which ones do you have? HPQ is the same thing as HD, D is the dimension, right? HD minus P, D minus Q. That turns out to be Serre duality, which we probably won't exactly talk about in this form, but that's what it is. And then HPQ is HQP, follows from the Hodge decomposition or otherwise. And then you also have the Hodge decomposition, which is the, I mentioned the first day, is the direct sum of the HQ of omega p's here, is the I cohomology of X, the topological cohomology. In the C at least. Now, with all of this symmetry, we don't have to compute all 16 of these numbers, okay? I'll tell you which ones are hard to compute. The first line is actually going to be not so bad. The second line, sort of not so bad, depends on the situation. The third line is a little unfortunate because that's starting to use this stuff here, and that means you have to do something to fix your presentation if you want it, to actually get those things. Omega 3 will do a different way in any case. But here you don't even need that because of the symmetry. If I know these 6 numbers, I know all of the other numbers, right? I think I got all the ones correct from symmetry. So that's that. So we just need to calculate those 4 numbers. Now, as I said, the first row is actually pretty reasonable. Yeah. And in fact, we don't want to compute all of those numbers in any case. So even h1 of omega 1, h2 of omega 1. Anytime we can cut that out, we're in good shape. Okay, so what's the situation here? Oh yeah, so that we do have the Euler characteristic going for us, right? So what's the Euler characteristic? The Euler characteristic of a sheaf is just the alternating sum of the hi of m's, of m tildes. But that thing is the Hilbert polynomial, the constant term of the Hilbert polynomial, essentially, of the module M. What's really cool about that is that the Hilbert polynomial is extremely easy to compute compared to anything else we're talking about. Okay? So if you can't do that, you might as well just start crying and go home or something. Okay, so at any rate, but if we know that, then what does that mean? That means that we can get rid of one of the computations of this because we know that number. So that's good. So let's see, what do we have here? Again, the first row, as I said, is the easiest over here. The second row, all of those are the cohomologies of omega 1, and we only need to calculate 1 if we know the Euler characteristic. So that's good to know. So we only need that 1, and then we have everything else. That's actually pretty good for 3 folds. For 4 folds, you have to also do omega 2. You have to do h2 of omega 2 or something like that. But in any case, it sort of goes on like that. Okay. We actually did the Hodge diamond already at the K3 surface then because we got all of those. And let's see, I did not write it down though. So it's basically, we'll do a more complicated one in a second of something else. So now let's put this back on for another example. Just want to show, actually, while that's going on, well, no, it'll be on in a second. I think it will be. So I have a bunch of code here that will actually calculate the Hodge diamond for a 3-fold just in this sneaky way. And it actually works reasonably well. So let's see how it goes. Just to keep things explicit. Okay. So here is a, whoops. This is the computation of omega 1 of x. So I've given an ideal I let S be the ring, I let R be the quotient ring, and then I just prune homology Varies of S, tensor R. The Jacobian of gens of the ideal, tensor R as well. That's exactly the same thing. And then we lift it back up to S. And even though I haven't proved it, that's enough. You don't have to add in the equations of I in this case. Okay, so that's omega. Let's see, do I actually compute it here? No, not yet. This cohom is a stupid little routine, but what it does is it basically, for a given module, it calculates all of the whole row. H0 of it, H1 of it, all the way up to H, the dimension of it. So let me get it down here and I'll discuss it then. Okay, so let's see, D is calculating the dimension of the module M. M is some graded module. You take the Euler characteristic of M, set that to be E. And then what I do is I actually make a list of all the HIs of the sheaf of M is M tilde. And I do it from 1 to D. With the idea that H0 is the hardest one to do. And so I'll let the Euler characteristic catch that one for me. That's actually a pretty naive approach, because if the projective dimension is small enough, then you can use it to get a different one instead. Anyway, so that's that. And then the other things are basically just doing the alternating sum to figure out what H0 should be. And then it prepends it to the list H. And that gives you the whole list of cohomologies. Now here's the Hodge diamond for a threefold. I just did it for the threefold, so I didn't have to. Here. Okay, this is going to be it. So basically, this does the same thing. It just it sets the ring S to be the ring of that, and R to be the quotient ring. It figures out the first row, figuring that that's going to be easy information anyway, so it doesn't worry about that. Then it calculates omega x to be using the omega from above, and then it does what we were roughly doing. It calculates the Euler characteristic, that's E. The next line is taking x of, let's see, number of generators minus 2 is n minus 1. So this is going to be calculating, that E there is going to be calculating H1 of the of omega 1 of x. And everything else, all the degrees are set up right. And then I grab from all the different places H10, these are the HPQs of these things. Except now for H11, I have to take the Hilbert function of that module E. And then I calculate H12, which is H2 of omega 1 by the Euler characteristic trick. And then I just write down all the values. So it's sort of like fairly simple, although looking a little bit long. So let's do another example. Here's the Fermat quintic in P4. Okay? So here's omega x, just to sort of give it. It's a little bit of a mess. But actually, if you look at it, it's a little hard at the moment because I have my print width set high. But again, you have these two Kazul blocks, just like before. And you can resolve that thing over S, and it has length 3. How many variables we're in? We're in P4, right? We're a cubic threefold. So, this has H0 of this is, we know it already, just like before. Cohomology of O of x here, a cohem of S to the 1 mod I, is 1, 0, 0, 1. So H0 of O of x is 1, that's good, that says it's connected. Nice to know that. H1 of O of x and H2 of O of x are 0, and then H3 of O of x is 1. So it's not rational. Okay, so now we use that Hodge diamond 3 routine here, and there's the Hodge diamond for it. So H11 was 1, and H2 of omega 1 was 101 dimensional. Now, if you actually go through and compute all these things, it's a little bit more of a nastiness. Oh yeah, let's do the second exterior power. So I take the exterior power of 2 of that omega x, and then I resolve it. This will tell us how bad of a presentation it is. If it goes way too far back, then maybe I can improve it. And sure enough, it goes back 5 steps, and it's relatively large. I don't want to really look at it. Oh yeah, let's just do this one then, I guess. So if you take a random quintic and take its Hodge diamond, it takes a little bit more time. There you have it. And then you can also do it for random, I mean, you can do it all these things. Oops. And then that works fine. Okay. Maybe it works fine. We'll see in a second. Okay. I don't remember it taking that. Oh yeah. So there, H3 of O of X is 5-dimensional, and so on. 255. There's really great symmetry in these things. But again, that's probably something you maybe know more about than I do.
Was that really random, the one you showed just now?
I hope it was random. I did. Actually, that's a good point. So how do I get random things? On this line here, you do a random s to the 1, s to the minus 6, and what it does is it makes a random homomorphism from those two free modules, graded homomorphism. So that should be a degree 6. So this should be random. Now when I say random, that's an excellent question. I'm choosing the rational numbers to have, I believe, the default is to have the numerator and denominator be 10 or less or something like that. So I don't know, is that random enough for you guys? Yeah, maybe not. Okay, anyway, whatever. Okay, so there you.
I just didn't know that if you chose a random one, they would have such large H1 omega 2.
Actually, this is going to be true for any of them. Yeah, it's invariant of it. So these things can be computed just from the degree.
The random. Okay, yeah.
These numbers are very cool, though. Yes.
So how do you improve the presentation of a module series?
We're going to talk about that in 3 minutes. Okay, maybe next time. But anyway, let's actually see what we got going here. Oops, I didn't really show you that one. Okay, let's turn that off. I don't think there's anything new there. That's just the numbers. And then here was the formula for calculating h1 of m tilde for h1 of omega x was this dimension of x3 in degree minus 5. This is how it worked out. When I end at 320, right? Yeah. Okay. So we're gonna next time we'll start with the improvement of presentation. So I guess I'm going to end with one conjecture here. This is a cool concept, this rationally connected stuff. Okay, so suppose I have a smooth projective variety. It's called rationally connected if there's several different versions of it. You don't have to take every pair. You can take 2 generic points or something like this. But if I take any 2 points on it, then there exists a rational curve connected. You can even have it. You can have it be a chain of rational curves, or you can have it be a one smooth rational curve. Whatever. But at any rate, there's say a rational curve on it. Now, let's not say it's smooth. Okay. So it's just some rational curve, possibly singular, containing it. So that's rationally connected. These things have been really important lately. They have really nice properties compared to things like rational varieties. These things behave extremely nicely in flat families, and this is sort of what basically Mori and Kolar and these guys have used to great advantage. Actually, a lot of other people too. Oh yeah, I'm not going any further than this. Okay, so here's the conjecture. And my understanding is that it was the following. Mori was giving a talk. This is when Mumford was still doing algebraic geometry. And he says, well, is it the case that x is rationally connected if all of these h zeros? Now, let's see if these things are 0. I take omega 1 of x. Now, I tensor it with itself. And I tensor it with itself again, and so on and so forth. I take all of those. Is it true that if x is rationally connected, if and only if, those are all 0? For all m greater than or equal to 1. And so now I don't know who it goes under as far as conjecture name, but it's one of these two guys. And the one direction is very simple. If those numbers are if there's any one number that's non-zero, then x cannot be rationally connected because you can take that differential form, pull it back, to the P1 that you have, the line that you have between your 2 points, which is it has to be one that's non-zero, and consequently that is a problem because there are no global differential forms on projective line. So that's an issue. But this is a really poor conjecture, okay? Why is it bad? I mean, look at this. It says for all m greater than or equal to 1. There's no bound on what m. No one has any concept, actually, whether there people sometimes, or at least some people think that maybe that if I restrict myself to 3 folds or 4 folds or any specific dimension, I have a uniform bound m for all such things. But other people, a little more pessimistic, say, well, maybe the bound will depend on each x or something. But no one has come forth with any, at least as far as I know, has come forward with any possibilities for what this is. And it seems like it's sort of a good problem, right, for, I mean, here's the real problem with it. There's been some really smart people that have looked at this one. So it's not going to just fall trivially, okay? So, although you never know. So, okay, anyway, it's now 3:19 if I read that in a funny direction, so I guess that's a good time to stop.